In chemistry, a weak base is a chemical base that does not ionize fully in an aqueous solution. As Brønsted-Lowry bases are proton acceptors, a weak base may also be defined as a chemical base in which protonation is incomplete. This results in a relatively low pH compared to strong bases. Bases range from a pH of greater than 7 to 14. pH has the formula. Weak bases will have a higher H+ concentration because they are less completely protonated than stronger bases and, therefore, more hydrogen ions remain in the solution. If you plug in a higher H+ concentration into the formula, a low pH results. However, pH of bases is usually calculated using the O- concentration to find the Po first. This is done because the H+ concentration is not a part of the reaction, while the O- concentration is. By multiplying a conjugate acid and a conjugate base, the following is given. Since then, by taking logarithms of both sides of the equation, the following is reached. Finally, multiplying throughout the equation by -1, the equation turns into. After acquiring Po from the previous Po formula, pH can be calculated using the formula pH equals pKw Po, where pKw equals 14.00. Weak bases exist in chemical equilibrium much in the same way as weak acids do, with a base dissociation constant indicating the strength of the base. For example, when ammonia is put in water, the following equilibrium is set up. Bases that have a large Kb will ionize more completely and are thus stronger bases. As stated above, pH of the solution depends on the H+ concentration, which is related to the O- concentration by the self-ionization constant. A strong base has a lower H+ concentration because they are fully protonated and less hydrogen ions remain in the solution. A lower H+ concentration also means a higher O- concentration and therefore, a larger Kb. NaOH is a stronger base than 2NH, which is a stronger base than NH3. As the bases get weaker, the smaller the Kb values become. Percentage protonated. As seen above, the strength of a base depends primarily on pH. To help describe the strengths of weak bases, it is helpful to know the percentage protonated, the percentage of base molecules that have been protonated. A lower percentage will correspond with a lower pH because both numbers result from the amount of protonation. A weak base is less protonated, leading to a lower pH and a lower percentage protonated. The typical proton transfer equilibrium appears as such. B represents the base. In this formula, B initial is the initial molar concentration of the base, assuming that no protonation has occurred. A typical pH problem. Calculate the pH and percentage protonation of a 20 m aqueous solution of pyridine, C5H5N. The Kb for C5H5N is 1.8 x 10⁻⁹. First write the proton transfer equilibrium. The equilibrium table, with all concentrations in moles per liter, is this means, 0.095% of the pyridine is in the protonated form of C5H5NH+. Examples: alanine, ammonia, NH3, methylamine, CH3NH2, C5H8O2. Other weak bases are essentially any bases not on the list of strong bases. Simple facts. An example of a weak base is ammonia. It does not contain hydroxide ions, but it reacts with water to produce ammonium ions and hydroxide ions. The position of equilibrium varies from base to base when a weak base reacts with water. The further to the left it is, the weaker the base.